In this video, we're going to talk about diabatic processes and how they are related to our upper-level positive PV anomalies and the overall life cycle of our mid-latitude cyclones. And so after cyclogenesis and cyclones develop, typically we have a certain amount of rising motion, and if there's enough moisture, clouds form, maybe some precipitation falls. And as a result, we violate our basic PV assumptions of it being an adiabatic frictionless flow situation. So what happens, and what is the influence of diabatic heating? We're going to begin by going back and considering our initial PV equation. And so let's recall that PV equals minus G times the quantity zeta theta plus F times d theta dP. We can rewrite this equation to make it a little easier for us to suss out the diabatic processes. And so we're just going to rewrite this equation in a slightly different way to then move forward. So minus G times the quantity F times K hat plus del cross V horizontal dot theta, or del theta. So we are simply here restating our original PV equation in a slightly different way. This is in a more three-dimensional sense, if you will, but still in our 2D framework, but just written in a way that is more extensible. In order to assess the diabatic effects, we would need to take the total derivative of this PV equation. Since this is synoptic meteorology and not dynamic meteorology, we are not going to do that today. We're just going to assume we understand how to get from A to B and posit the result. If we were to do so, we would find that ddt of PV equals minus G times the quantity, the absolute vorticity, eta, dot del theta dot. And so the theta dot here is what we're really getting towards here in this idea of the diabatic heating rate. So eta sub A is our absolute vorticity. Vector, right, since we have the vector symbol on top. And here we have our vector quantity of our diabatic heating rate. Now, what we're really thinking about here is we are only thinking about the vertical component of this diabatic heating rate. And so really we just want then the K hat component. And so let's go ahead and write our K hat component. So ddt of PV from our K hat component is approximately equal to minus G times zeta plus F times d theta dot dP. This solution looks awfully similar to our regular PV solution, and in fact we have that up here, and it is with one crucial difference. Instead of looking at just the rate of change of theta with height, or with pressure, we are looking at the rate of change of our diabatic heating rate with respect to pressure. And so otherwise we get a very similar solution here, and this is going to allow a very elegant reading of this idea of how the diabatic heating rate influences our PV distribution throughout the atmosphere. And so recall that previously in our PV situation with this equation is true only under the circumstances where the flow is adiabatic and frictionless. And so that the only way to change our PV distribution when it's adiabatic and frictionless is to do advection, of which we talked about how we can get cyclogenesis through that framework. Now we want to assess how does the diabatic heating rate and the presence of clouds potentially influence our PV by changing our PV distribution. And so we're going to look at some figures from the Martin textbook to illustrate this concept. And so if we have a diabatic heating max here in the center, which we can think of this as an area in which we have a cloud, we want to assess what is changing about our situation as we go up to this max from the surface and from this max aloft in the atmosphere. And so let's consider then these two levels. We're going to start here with our surface to our maximum level. And what we want to do here is we want to assess what is d theta dot dp. And so we know as we are decreasing in pressure, right? Because as we go up in the atmosphere, we're decreasing with pressure, right? As we go up from the surface, we are getting to lower and lower pressure. Our theta max is increasing. And so our PV then, if we think about our equation, let's go ahead and rewrite our equation here, right? We have our ddt of PV k hat is equal to minus g zeta plus f d theta dot dp. And so just looking at this influence here of the vertical gradient in theta dot, we are going to then have minus d theta dot dp as greater than 0 in this frame, because this minus ddp then gets us into that positive framework of moving up in the atmosphere. And then our theta dot is increasing as we go up towards the max. And so if this is greater than 0, if this component is greater than 0, and we assume that our absolute vorticity is greater than 0, our value of g then is greater than 0. We're taking care of this negative sign with the ddp. That means we are going to generate PV below. And so in this area, down here, we have ddt of PV greater than 0. We are generating PV. We can potentially generate more positive theta anomaly as a result of this diabatic heating process and the fact that it can physically change our PV situation. Now let's look aloft. As we go up in the atmosphere, our sign of minus d theta dot dp changes, that this is now less than 0. Because as we are moving up, minus ddp is positive, but theta dot is now going from a maximum to something less. And so through time then, our PV is being destroyed above our maximum in diabatic heating. And so if we have our cloud here in the center, which we know is releasing latent heat into the atmosphere, we can generate PV below, create a stronger PV-like anomaly below, and we are going to destroy PV aloft. And so you might be saying, well, what is this going to do to our overall cyclone? And where would this actually happen with respect to our cyclone? And if we think about our typical mid-latitude cyclone, right, we're going to have that either in the warm sector or just to the east of any sort of upper level anomaly. And so if we go ahead and look at figure 912 from the Martin textbook, we can see this in reality. And so if we have our cyclone and our cyclonic circulation associated with our low-level cyclone, we get our rising motion. Our rising motion then induces a cloud. And so we get our cloud. And from our cloud, then, we generate PV below, ddt of PV greater than 0 below, and we get ddt of PV aloft less than 0. And we create this almost extreme anomaly here as we go across on a particular level. So if we look here at some sort of level, we have a stronger positive PV anomaly as the result of having this mid-level diabatic heating with our cloud maximum, such that we create a greater slope to this surface, which means we're going to create stronger cyclonic circulation associated with this anomaly, creating a stronger cyclone. And this diabatic heating in the center is acting as a way to couple our low-level anomaly with our upper-level anomaly when we are having this westward tilt with height or up shear tilt with height. And so the diabatic heating process here is adding on. It's an additive effect, similar to what we see with our QG dynamics when we add in those terms to, say, our QG omega equation, and that they basically double down where we have rising motion. If we have enough moisture to produce clouds, that's going to increase the chances of rising motion due to the diabatic processes going on, heating the mid levels of our atmosphere. Same thing here in our PV perspective. And so this is just a beautiful way of looking at the same process, getting the same result through a different lens. One way we can see as our cyclones are wrapping up and this diabatic heating is being incorporated within the center of our cyclone is by a very distinct look to our upper level PV pattern. And so here we get something called the treble clef signature, which is basically the bottom part of our treble clef. And what we notice here is we have a center part where we kind of have a diminished amount of PV. This diminished amount of PV is due to diabatic processes. And one way we can think about this is the wraparound region of our mid-latitude cyclone, such that we have these diabatic processes happening in mid-levels, causing a destruction of PV aloft, and is an indication here that we may be near or in an occlusion process within this system. Another thing that this is a result of here in this PV notch, as it's sometimes called, is a trough of warm air aloft. Again, this idea of lifting a layer of air within our cyclone, typically happening in and around that occlusion process. And so this diabatic process absolutely helps to couple together the upper level positive PV anomaly with our low level positive theta anomalies to help maintain these systems through the life cycle of our mid-latitude cyclones until such time as we reduce that westward or up shear tilt of our cyclone, and we get then PV destruction within our cyclones. Hope this helps understand a little bit more about how everything is related with our PV structure here, and how we're not getting a different answer from our QG dynamics, but this different lens allows us just a different perspective to seeing what's really going on in the atmosphere at any given time. Thanks for watching.